So I want to speak to you today about two slightly related things that I've been working on. So the first is a bit of work I've done with Plotly about writing a Scala client. So this is a Scala library that lets you draw graphs on Plotly. And I could talk about this all day, but I'm sure you'd get bored by the third slide of code that I show you. So instead I'm going to show an application of this where I've looked at what made open source repositories popular on GitHub. So I work for ASI Data Science, which is a London-based data science consultancy, and I work there as a data engineer, and when I'm not doing that, I've written a book on using Scala in data science. It's a couple of years old now, and I maintain a Python library called jupyter-gmaps for visualizing geographical data in Jupyter notebooks. It's a lot of fun, and also the Scala Plotly client, which is what I'm talking about today, and I've been working on this with other people at ASI. How many people in this room have used Scala at all? All right, it's more than I thought. So I think Scala is fairly popular in data science, especially for building maybe larger data science applications, because it has great concurrency support, it has great native libraries for large-scale data processing like Spark, and it has access to everything that's been written for the JVM. So that's a host of very, very mature Java libraries. And so for all these reasons, I think Scala is fairly popular, especially for building larger data science applications once you go beyond the exploratory step. But one of the things that surprised me when I got into Scala, and that still surprises me today, is the lack of a good data visualization library. There's no matplotlib equivalent in Scala, and I think that was a surprise. I was coming from a Python world, and yeah. But I think the underlying reason for this is that data visualization libraries are hard to build. If you look at matplotlib, which is definitely one of the most successful Python libraries, data visualization libraries ever built, it has 19,000 commits. That's a huge amount of work. It's 2,000 more commits than Apache Spark, as in more work has gone into matplotlib than Apache Spark, which maybe intuitively seems like a larger project. And I think there's two reasons why data visualization, why data visualizations are hard to build. I think it requires the intersection of two very different skills. You need a very deep understanding of the problem domain of data and of how to visualize it. And I think it's telling that the original authors of matplotlib came from a science background rather than a software background. But you also need very good software engineering skills, and in particular you need a very good knowledge of the underlying platform on which you're drawing the graph. You need to basically get lines and dots in the right place, and that's non-trivial. And so finding people with the intersection of those skills is difficult. But what if we took a shortcut and let someone else do all the hard work? And this is where Plotly comes in. So Plotly doesn't need an introduction here in this conference, but as far as we're concerned, Plotly is just an endpoint to which you can send a blob of JSON that declares a graph, and Plotly will render it. Now, unlike data visualization libraries, Plotly clients are easy to build because you don't have to worry about how to best draw the plot, and you don't have to worry about how to actually render it in a browser. You just need to know how to generate the right JSON, and writing a Scala library that generates JSON is not particularly challenging. So this is what we did. This is an example using it. This is the only Scala code in this talk. But for those of you who haven't seen Scala, well, this is it. We're just generating some x's, then we're generating some y's. This is just y equals x with a bit of random noise. And then this is a bit where we're actually declaring the plot. And then we dispatch it to Plotly. And we've tried to have this nice declarative interface that should feel intuitive for most Scala programmers. And you do this, and you can then go on the Plotly website, and it gives you this graph, which is more or less what you expect. The client's not limited to just simple scatter plots, you can add styling, you can have multiple subplots in one figure, you can have surface plots, you can have bar charts, etc. So this is the Scala Plotly client, it's open source. I really enjoy working on data visualization libraries because what you have at the end is extremely tangible, it's very concrete. You implement a feature, then you can draw a plot that uses that feature. It's very tangible. You can show that plot to your girlfriend and she can pretend to be impressed or something like that. So come and contribute, it's open source. Alternatively, go and build your own Plotly clients in a language of your choice. It's a lot of fun and it's very easy. Like I said, I could carry on talking about this, but I think you'd probably get bored of me just showing graphs, so instead I'll look at an application, which is trying to understand why some repositories become very popular on GitHub. And so all the plots in this will be drawn with a Scala Plotly client, apart from two, which I'll point out. So the first thing to say is GitHub is huge. There's 35 million repositories. It's not far off 2 billion commits. That's a tremendous amount of work. It's the home of some of the most influential software projects. The Linux kernel, Docker, Rails have all in their own way changed how we write software. So there's some extremely popular projects, and one of the ways to measure popularity of a repository on GitHub is through stars. So if you're logged into GitHub, you can star a repository, which means that you think it's valuable in some way, and the most popular repositories will have thousands or tens of thousands of stars. But 82% of repositories have 0 stars, and 98% have fewer than 10 stars. So if your repository has at least 10 stars, it's in the top 2% of repositories. And we can try and be a bit more quantitative about this. We can draw a rank frequency plot. So this is where we take all the repositories in our sample. Our sample has about 1 million repositories in it. We take all the repositories, we rank them by stars. And that gives us the probability of any given repository having at least this many stars. And then we can draw this probability against the number of stars. We draw it on log axes, and we find that basically the distribution of stars obeys this nice power law from between 0 to about 200 stars, which encompasses about 99.8% of repositories. And then it tails off at the top end because you don't get repositories with hundreds of thousands or millions of stars, or at least very few. And because it obeys this nice power law, we can come up with nice Pareto-style 80-20 type metrics, except this is a 72-28 division. So the top 28% of repositories hold 72% of the total stars. Conversely, the lower 72% of repositories have just 28% of the stars. Now, I always find these unequal distributions, these uneven distributions, quite hard to understand. And so quite unintuitive. And so I think one way to gain intuition about it is to map it onto other uneven distributions that maybe we have more intuition for. And one obvious one is the income distribution. We're all familiar with what it means to have a 5-figure or a 6-figure salary in terms of where that places us on the global ranking of salaries, for instance. And like income distribution also obeys a power law, so we can do this, and it kind of makes sense. So to map across, we need a way to measure the inequality in this, and I've done this through the Gini coefficient. There's other ways to do this, but the Gini coefficient is just one way to measure inequality in distributions. So we find that the distribution of stars on GitHub has a Gini coefficient of 0.6, which by itself doesn't mean very much. But we can compare it to the world income distribution, which has a Gini coefficient of 0.8, or for most first world countries, the Gini coefficient is between 0.4 and 0.6. So that means that the Gini coefficient, that the distribution of stars is in some sense similar to one of the more unequal first world countries like maybe Italy or like the US, which means that if your repositories is in the 98th percentile, if it has 10 stars, then it's equivalent to being in the 98th percentile of salaries in the US. So it's roughly similar to having a six-figure salary, say. If it has 100 stars, so it's in the 99.5 percentile, I would imagine that's similar to having a seven-figure salary, approximately. So maybe that gives us a bit more intuition about this distribution, but what we really care about is why do some repositories become popular? And I think you can distill this to four rules, which are unfortunately not super easy to implement. The first one is people don't put stars on websites. So GitHub tries to infer what the dominant language of your repository is, and if it's written in a programming language, so something like Java or Python or whatever, then if it's in the 98th percentile, it'll have at least 19 stars. If it's in a markup language, so something like Markdown or HTML, it will have just 4 stars. And this doesn't just apply at the top, for the top 2%. It applies across the whole range. So again, this is the same rank frequency plot, but now split between repositories written in markup languages and repositories written in programming languages, and we find that consistently for the same level of popularity within their respective populations, a repository written in a programming language will have many more stars than one written in a markup language. There's a bit of noise at the top, but I think that's just because there's very few repositories with this many stars. The second rule is not all languages are created equal, at least in terms of getting stars. Again, if you're in the top 98th percentile, and you've written the top 98th percentile of repositories written in Go, you have 93 stars. If you've written your repository in Java instead, you have just 10 stars. So there's a huge discrepancy. And this, I think, this scale kind of aligns with, I guess, what intuitively you might think is the coolness of a particular language. For some value of cool, Go is definitely a more popular language than Java or C#, certainly in open source. Java and C# feels a lot more corporate-y, a lot more enterprisey. And this, again, doesn't just hold for the 98th percentile, it holds across the entire range. So this is, again, the same rank frequency plot, but you can see that consistently a repository written in Go will have more stars than a repository written in Java with the same level of popularity. The third rule is the harder you work, the more popular you're going to be. So this is not done on Plotly, this is a matplotlib plot, because I don't think Plotly lets you draw these histograms without the vertical bars, which are quite nice for representing distributions. So in blue, you have basically the distribution of all repositories, and you can see that there's very few repositories with many stars. This is a log scale, so this is a very, very low number. If you only take the repositories which have at least 100 commits, this really boosts up the probability of having more stars. And if you go to 1,000 commits, then it goes up even more. So the harder you work, the more likely you are to have lots of stars. The green line is a bit more noisy because there's just fewer repositories in the sample. But not all languages are created equal, and if you have 1,000 commits and you've written it in Go, then you have better than even chances of having 50 stars. It's a bit lower for Scala, and then a bit lower for JavaScript and Python, and I'm sure if Java were on that chart, it would be even lower. And that, again, doesn't just hold for very high commit repositories, it holds across the entire range. So the more commits you have, the more likely it is to be popular across, that's true across all languages, but Go is definitely much more popular. The last rule is make it approachable. So there's different things you can do to make it approachable. I've looked at mostly README here. Again, this is a probability distribution of stars. If you don't have a README, the repositories never get above about 20 stars, whereas with a README, you're much more likely to have a high number of stars. There's other things that you can do to make it approachable, which have a weaker effect, like having a home page. You can set up a home page in GitHub and things like that. Cool, so to summarize, Websites don't get stars. There's definitely, if you really want to maximize the number of stars, which is maybe something you want to do, maybe not, there's some languages which do that a lot better. The third rule is work really hard, put in lots of work, put in lots of commits, and also work hard to make it approachable. For a bit more levity, I have all these repositories, all these commit messages. You can see how often people swear in a particular, for repositories written in a particular language. I'll let you interpret this yourself. Actually, what I find most surprising about this chart is at the bottom of the scale here, languages which have developers which are apparently surprisingly chilled out, like PHP and Java. That certainly surprises me. So I've done the bulk of the work in Scala with a Scala Plotly client. I did some initial data exploration in Python. It's been a lot of fun. I used a data science platform that we're building at ASI Data Science called Sherlock ML. This is in beta, so if anyone's interested, I can give you invitation codes. Cool. Any questions?
Thank you for the insightful presentation. So one of your conclusions is that the more commits you have, the more stars you have. But I wonder if it's just pure correlation or there is really causation, because it might be that the more reward you get by people asking you questions, raising issues, then you get more, you kind of get to more work and you do more work. Is it, I mean, to me it looks a bit dubious. And did you have a chance to look at the collaboration, kind of whether the popularity grows with the number of different users committing to the same repository? Thank you.
Thank you. Yeah, you're completely right that there's virtuous cycles, I think, between the popularity and the number of commits. It's probably quite hard to disentangle these. There is a very strong correlation between the number of committers and the popularity. And in particular, there's a strong, the more popular you are, the more likely you are to have more core committers. I don't have the plots in this to show it, but there's a strong correlation. Also between the number of stars and the number of forks, it's extremely strongly correlated. Cool. Yes.
Very good presentation, thank you. First question, is this work on GitHub?
As in the source code?
Yeah, for your analysis.
It is not. It should be. It will be.
Okay.
It is not right now, but thank you.
The other question was, where you had the more popular languages as Go and Scala compared to like Python and JavaScript, which seems like counterintuitive to me. So I was wondering if it's possible, like if it's been normalized by the number of repositories using it, because I have to think that there's much fewer Go and Scala compared to JavaScript and Python.
There are. I think it's. I don't think it indicates so. I mean, it's normalized in the sense that the number of. I mean, this is like a per repository. I don't see how you necessarily normalize this if there's more repositories in a particular language. It's certainly true that there's like 10 times more Python or JavaScript repositories than there are Go or Scala repositories. And so in that sense, repositories well, it's certainly true that the more niche languages tend to get more stars per repository. I think because they have that, I guess, exotic appeal that maybe the more mainstream languages don't. if you want to maximize the number of stars, that doesn't change the conclusion, right? You should still write it in one of those languages that do that. Cool. Thank you.